Hello, everyone. In the last video, we defined what the span of the vector is, and we discussed the relation between the span of a vector and consistency of a certain linear system. Today, we'll pick it up from there, and we'll define a new concept, that of a generating set, which is also related to this circle of ideas. But before moving into that, let's just wrap up what we know so far. And I encourage you to look back at the previous examples to see that what I'm about to explain to you makes sense, and we've seen it happen so far. So what we did in the last video, and we'll keep doing today, was to convince ourselves of the following theorem. Whenever we're given a matrix, m by n, then there are many equivalent ways of saying the same thing. And depending on our situation, one of them may be more efficient or less than another. So it's good to know that all of these conditions carry the same amount of information. The first of these conditions is the linear system with the associated matrix A has a solution for every possible vector of constants B. So that's a very important part of this condition. The system being consistent no matter what we stick in the vector of constants here. That is the same, it's equivalent to saying that every possible choice of V in Rm is a linear combination of the columns of A. In other words, and this is the terminology we introduced in the last video, the span of the columns of A is the whole space Rm. Another equivalent way of saying conditions A and B is that the rank of A is exactly n. The condition on the rank ties up the first two conditions that are very abstract in some sense to something very concrete, which is the number of pivot columns in our row reduced echelon form. In fact, the other two conditions are similar to condition C in that, because they involve the number of rows of zeros of our matrix. If our matrix has no rows of zeros, or if every row of A has a pivot position, then those are equivalent to the rank of A being n and the linear system with A as a matrix being consistent all the time. Let me just comment on condition C, which is, as I said, in some sense, the more conceptual, the one that ties the span of columns to something very practical, which is the reduced row echelon form. If the rank is not n in a matrix that has, let's look at the size, exactly m rows, then the only way that the rank is not m is that there is a row of zeros in the reduced row echelon form. However, if there is a row of zero in the reduced row echelon form of A, whenever I augment the matrix A with a vector V, I may get an inconsistent system for some choices of V. So having a rank different from n tells me that conditions A and B may not hold all the time. And that's the same. That's exactly what this theorem captures. The rank equals n tells you that the linear systems will be consistent all the time. Another note that I want to point out is that condition E and condition C are the same, are equivalent, because the number of pivot positions in a matrix with m rows, well, in general, is the same as the rank of the matrix. And in a matrix with m rows, saying that every row has a pivot position is the same as saying that the rank is n. So this theorem ties up what we've been doing so far. The reason why we care about a result like this is that our next definition is going to be that of a generating set. We talk about generating sets when a set of vector spans a whole space. In particular, more precisely, we say that S is a generating set for Rn, where S is a set of vectors, where when the span of S is the whole Rn. Let's have a look at that in action in an example. This S is a set of vectors with 4 entries, so certainly it is a subset of R4. Now the question is, if I take the span of S, do I get the whole R4? In other words, is S a generating set of R4? Well, we can try and do it by our theorem, by the equivalence between condition B and C. The span of S being R4 is the same as the rank of the matrix being equal to 4. So this is condition B if and only if C in our theorem. The matrix A here is the matrix whose columns are the vectors of S. So the matrix will be 1, 1, 0, 1, 1, 2, 3, 4, 2, 0, 0, 1, 1, 0, 1, 1, and 2, 1, 1, 1. For now, we don't have a fast method to compute the rank of a matrix. Therefore, the only way that we know is to compute the reduced row echelon form of that matrix. I'll skip those steps now because we've done it many times, but here is the answer. So if this is our matrix A, its row reduced echelon form looks like this. Now you see from here that there are 4 pivot positions. There's as many as the rows, so the rank of A is indeed equal to 4. And that implies, by what we said just now, that the span of the set of vectors S, which are the columns of A, is equal to R4. Now, the next question I'm going to ask is, can we do a little bit better? Do we need all of the 5 vectors that are in S to generate R4? Is there a way that we can get rid of one of them and still get a generating set? So here's the setup that I would like to try. Let's define a new set, S twiddle, by keeping the first 4 vectors in S. And I'll give them names so that I don't have to keep writing them out. I'll call them V1, V2, V3, and V4. As I said, this is exactly the set S, but let's remove the last vector, which I'll call U. Now, the question is it true that the span of S tilde is the same as the span of S, which is the same as R4 as we saw? The way we can make sure of this is the following. So suppose for a second that it is. The computation that we would like to do is this. If we know that these 2 spans are the same, then it means that for every vector W in R4, I can write W as a linear combination of elements of S. S is the set whose vectors are V1, V2, V3, V4, and U. And also as a linear combination of elements of S twiddle, using just V1, V2, V3, and V4. That's our assumption, that the span of S twiddle is the same as the span of S, and it's the same as the whole R4. But then if I write W in these 2 different ways, what do I get when I subtract them from one another is the following equation. I get 0 on this side because it's W minus W, and then I'll have C1 minus D1 times V1 plus C2 minus D2 times V2 all the way up to, well, maybe I can just write them, C3 minus D3 times V3 plus C4 minus D4 times V4. And then I must not forget the last summand MU. There's no U in the second row, but there's mu in the first. So what does this equation mean for now? Well, I can solve for u. So allow me to do that and take this mu, and I'll put it here on this side. And of course, you know better than me that when I do that, I need to switch the sign there. So the next step will be divide everything by minus m. And the equation that you get is something like this. You see that I'm dividing everything by m, all of the coefficients, and then the minus sign is actually changing the sign of the numerator. I'm going from c1 minus d1 to d1 minus c1. So I was able to write u as a linear combination of the vectors v1 through v4. And that's what I've written here with this vector x, whose entries are d1 minus c1 over m, d2 minus c2 over m, and so on. So the question is, if the span of S twiddle is the same as the span of S, then I should be able to solve this linear system. I should be able to solve U equals the matrix whose columns are V1 through V4 times X. That's the next question. Can we do that? And in fact, we already did. Let's have a look back at what we wrote above. We had a matrix A whose columns were V1, V2, V3, V4, and U. Now we can reinterpret that matrix A as the augmented matrix of a linear system whose columns are V1 through V4 and whose constant term is U. When you think of this matrix like this, well, the reduced row echelon form doesn't care how you think about the matrix, so you'll get the same reduced result as before. But interpreting in this new way means that we can actually write U with the coefficients that are written here. So U is equal to minus 4/3 V1, minus 4/3 V2, minus 9/6 V3, plus 5/3 V4. The upshot is that U belongs not only to the span of S, but to the span of S twiddle. And therefore, the span of S twiddle must be equal to the span of S. Let's make this more rigorous in the following theorem. Here's what we just did, except now it's stated in general. Suppose I have a set containing vectors v1 through vk and then another vector u, and a similar set of vectors S twiddle where I only have v1 and vk. Then the two spans are the same if and only if u belongs to the span of S twiddle. We saw that happen in an example, but the reason why this works in general is a very similar computation. If these two spans are the same, then you may pick a W for which, and this is a little, we need to be a little careful. At some point in the computations above, we divided by m. So we need to make sure that we can pick a W for which m is non-zero, but we can do that. There are vectors like that in this span. And we do the same thing as before. So we take the second row and subtract it from the first. And then we solve for u, which shows that u will belong to the span of S twiddle. So this theorem works in exactly the same way, but in more generality than what we just saw in the example. Let me finish with this remark. And this is something that we'll use as a stepping stone for where we're going to go next. If we are in a situation where we have these two sets, v1 through vk and v1 through vk minus 1, so S twiddle is obtained by removing one vector from S. If the span of the two is the same, then I can write, by the theorem that we just quoted, the last vector, vk, so the the vector that is missing from S-twiddle, I can write it as a linear combination of the first few vectors, a1 v1 plus ... ak minus 1 vk minus 1. Now, if I move this vk to the other side, I get an equation that is very innocent looking, but it will lead us to the concept of linear dependence. So let's have a look at this equation here. What we did was to write something missing in this equation. There should be a vk minus 1 there. We can write the vector 0 as a linear combination of v1 through vk, but we know for certain that one of the coefficients of this linear combination is non-zero, namely the coefficient of vk, which is -1. This is just an isolated remark for now, but we'll see next time that this idea is what will motivate what we'll do next, which is the definition of linear independence. I'll see you in the next video.